Assalamualaikum warahmatullahi wabarakatuh. I am Hendy. Welcome to Introduction to Artificial Intelligence. And this time we will discuss about nearest neighbor. So nearest neighbor is one of the algorithms for machine learning. So what is the nearest neighbor? So imagine that a computer is tasked to compare or to learn what this is. Okay, so we know that this is total, right? So the previously we have learned about decision tree. Decision tree is good for samples who have limited and discrete attributes. Okay, so what I mean by discrete attributes is that you have like previously you have GPA, you have psychology, you have interview, and then for each of the attributes you have discrete options like the GPA is high, medium, low, and yeah, similar like that. However, there are problems that have lots of attributes and the tree will be too complex if we are using decision tree or ID3 algorithm. So for example, image classification. So when you think about it, what is an image? An image is composed of lots of pixels, right? So for example, this one is an image of letter E, and even in this very simple image, there are 10 by 10 pixels. So how many pixels in total? We have 100 pixels, and each one is either 0 or 1 for black and white, and then we have 20 data, and we have 4 classes. So can you imagine using ID3 with information gain and Shannon entropy for 100 attributes? That will be too much. And this is just a small image. Can you imagine if you are doing image classification with a HD or full HD image and color image? That will be very exhausting, yeah, using decision tree. Okay, so what can we do about this? So this is how character recognition works. It's part of image processing. So for example, this is character E, and we have 10 pixels wide and 10 pixels of height. And then in the two-dimensional array, we have zeros for these blanks and ones for the black pixels. Okay, and to make it easy, because we are dealing with attributes or input attributes, let's change this into a one-dimensional array. So instead of 10 pixels by 10 pixels, now we have 100 attributes, okay, from the first pixel here to the last pixel here. Okay, so now we have samples with 100 input attributes. So how do we manage this in a character recognition dataset? So as you can see, we have 20 data samples. We have 20 data in the training dataset. And then we have 4 classes. Okay, we have 4 classes, and for each of the class we have 5 different samples or variations, and we have 100 attributes or 100 dimensions. So let's say, what if we try to use ID3, the decision tree algorithm, to build this classifier of learning? What will happen? So, for example, we have done the Shannon entropy calculation, we have done the information gain calculation, and that means first, let's say, first we will decide from the pixel number 48 whether this is 1 or 0, and if it's 1 it becomes, for example, E. If it's 0 it becomes, well, another decision tree for pixel 20, and so on and so on. Now, because we have 100 attributes, it's possible that this complete ID3 decision tree will become 100 levels deep. So it will be too deep because our input is 100 dimensional. So this is not efficient. Enter nearest neighbor. So nearest neighbor is an algorithm that is relatively simple, that stores all of the available cases or training samples, and then it will classify or predict new cases based on a measure of similarity. Okay, and this technique is non-parametric, and the other names of nearest neighbor is like memory-based reasoning, example-based reasoning, and so on. So we have two processes here. First, we will train all of the training data and the labels. So the labels will be, in this case, for character recognition, it will be E, F, or G, or O. And after we have memorized all of the training data and labels, we will go to testing process. So in the testing process, we have new data, we have new image, and we want the algorithm to predict what character is this image. And nearest neighbor for calculating the similarity or distance between an image to another image, we can choose between usually L1 or L2. If L1, then we will use Manhattan distance. If L2, that means Euclidean distance. So Manhattan distance, the formula is like this, and this is basically just the subtraction, the absolute subtraction of the pixels, okay, between the first image and the second image, and then sum all of it together. And in Euclidean distance, the difference of each pixel will be squared and then summed and then square root. Okay, so we will see how to calculate this in the example. Okay, so for example, we are using L2 or Euclidean distance here. So how do we measure this similarity? How do we measure the distance between this test data and this training data? So you can see here, so we need to do this for all of the pixels. So this is the first pixel. So what is the difference between this and this? 1 and 1, the difference is 0. And then we square the difference. Okay. First, the difference is 0, we put it here. And then the difference between 1 and 1 is 0, we put it here. And let's see which one is different. This one is different. Okay, this is 1 and this 0, so the difference is 1. So we put all of the differences here, And then for each of the differences, we will do a square. Okay, so this one we do a square, this one is square, square, and so on. And then we sum all of them, and then we do square root on all of this. So because we have 1 squared is still 1, so 1, 2, 3, 4, 5, 6, 7, and that means we have 7 here, and then we square root. So this is a square root of 7. So this is the most important concept in nearest neighbor. You need to be able to calculate the distance between two sample, two data. This is using L2 distance. What if we are using L1 distance? So the basic operation is the same. You need to do the value differences, but the difference, but now instead of doing the square, you just add all of them together. Yeah. Using absolute, so no negative sign here, just positive sign. So that means the L1 distance is 7. Okay. And what happens if we have something like this? This is the difference between this one and this one, and the difference is 3. Okay. So now that we have known how to calculate the distance between two sample data, the algorithm itself, for all of the test data, okay, so this assuming that you have more than one test data. So each of the data that you want to test, you loop through all of the training data. So in the previous example, we have 20 training data. So we loop through all of the 20 training data. And then we calculate the distance. Calculate the distance between what? Calculate the distance between training data, that training data here, and the test data. And then we will choose the closest training data, in this case X, and then that training data, the label of X will be the label of the dataset A. Okay. So how it works is that we are trying to find the most similar training data to the test data. Okay. So let's see how this works in practice. Okay. So let's say now we have 16 data as training data. So we reserve the other 4 as test data. And then we reshape that into vectors, meaning that we put each of these data into one-dimensional features, okay, one-dimensional attributes. So this will be 100 attributes for each of the data. So we still have 16 training data, yeah? 4 training data for class E, 4 training data for class F, 4 training data for class G, and 4 training data for class O. Okay, and then we save it to the database or we save it to the memory. And that's it. This is the learning or training process. It really is. The next part is for the prediction or testing process. Okay, so now we have a new data that we don't know what the class is for this data. So let's see if using nearest neighbor we can classify this data. So what we will do, first we change the new data into one dimension, just like we do for the training data. The test data we change to one dimensional, just like we do for the training data. And then we calculate the distance of this test data to each of the 16 of the training data. So which formula that you will be using depends on you. If you use L1, that will be Manhattan formula. If you use L2, that will be Euclidean formula. Okay. So after using that formula, so now we have the distance between this test data to each of the training data. So this is the distance for this for training data of E here. These are the distances. This distance is using Euclidean, yeah, L2. And this is also the distances for F. These are the distances for G. These are the distances for O. Now, after we have all of the distances, what we need to do is we sort the results of the distances from the smallest to the highest. So this is the smallest one. And if you see here, it's quite obvious, right, that this test data is E when you look at it visually. And based on what you see here, nearest neighbor is pretty good, right, for classifying, because the classes with the smallest distances are actually E. Okay. So if we pick one, the closest training data, or the distance with the smallest distance, that means this training data is E. So that means the program can give the result that this new data, this unknown data, has a class of E. Okay. So that's how nearest neighbor works. And we return the label of the closest data, which is E, this one. Okay. So let's take a look at another example. So what if our new data is like this, okay? And then we do the same process as before, and then we sort it. For this one, we have the smallest distance is 1.4 and the class is F. So this is pretty good, yeah. And what about the G1? The closest one is 1.7 and it is G, okay? And for example, about this one is quite ambiguous, yeah, whether this is G or this is O. So in this case, it's closest to the O, okay, 1.4. But is there a problem with nearest neighbor? Okay, the training speed. Okay, the training speed is basically no training because we just save all of the training data to the storage. And how about testing speed? The testing speed is linearly slower according to the size of training data. So the more training data you have, then the testing speed will be slower as many times of the training data. Okay. And what happens if we have a new data like this and there are two training data with the same distance, and one is G and one is O. One possible alternative will be just pick either one. Okay, so that means sometimes the program can result in G, and sometimes the program can result in O. Is there a better alternative, or is there a different alternative? Yes, there is a different alternative. Okay, and okay, this is another example where we have these three distances are the same, 2.4, but 2 is in E and 1 is in F. Okay, so which one do you think it should be? Okay, I think it should be in E, right? But how do we program the nearest neighbor so that it picks E instead of F? If you notice, the E here has two training datasets with the small distance, while F only one. Okay, so that means we can choose the training data with the smaller distance with the most number of matching training data, and that is how we get to K nearest neighbor instead of just nearest neighbor. So nearest neighbor is one of the nearest neighbor, and then when we add K, that means we choose many neighbors. Okay, we choose several neighbors to determine the class. So basically the neighbors do the voting. Okay, we do the voting. So for example, if we choose K equal to 3, then after we do the distance calculation, for example, we have these results, and then we choose the three of the closest uh, training data. Okay, so that means we have this one O, and we have this one G, and one more. Okay, one more will be G also. So which one do we pick for this? If the K is 3, then we pick G, because G has 2 votes while O has only 1 vote. Okay, so we sort it like this, and then based on the 3 of the smallest distance, we vote, and G has 2 votes, so G wins. Okay, 2G and 1O. Okay, so the result will be G. Another example, we have this one, and then the result is like this, and then we do the sorting. So we have E, and then F. So by voting, because we have two E's and only one F, the result will be E. Okay. Do the same thing again. Okay. Now what happens if this is what's happening? Even if we sort it, then yeah, it depends on the sorting. You can get E or you can get F. Okay. Okay. So this will depend on the sorting result. Okay. And so if that happens, what is the solution? One of the alternatives is that we can increase the value of K. So we sample more data. So if we choose K to 5, then it means we have 3 E's and then 2 F's. So the result will be E. Okay. So how do we choose the best K for K nearest neighbor? Okay. Now, how you choose that is using validation. Okay, so you do several experiments, and then you determine or you calculate the difference between the real classes and the predicted classes. So you do it for 1, for k equals to 1, for k equals to 2, for k equals to 3, and so on. Then you can plot it in this graph. And this one is the misclassification error. And then you choose k with the least number of errors. So for example, a good k here will be k equals to, this one maybe 7 or 8. I think this is 7, yeah, because it has the lowest misclassification errors. Okay. And how about the best distance to use, and how about the best k to use? This is the hyperparameter that you can use for k nearest neighbor algorithm. And these hyperparameters you can experiment and plot using the previous technique. And then this hyperparameter is very problem dependent. Yeah. What I mean by problem dependent is that if you use a different training data set, then maybe the hyperparameter that is good for one training data set, maybe it can be bad for the other training data set. So you must train the hyperparameter. You must experiment with the hyperparameters in your training data set and try them all out and see which ones will work best, whether it's using L1 Manhattan distance or using L2 Euclidean distance, whether it's using the k value from 1 to 2, 3, 4, 5, and so on until you find the best values.